Okay, well, welcome everyone. Today we have the next installment in the IFRR Robotics Colloquium. And we are fortunate to have a fabulous speaker, which, unfortunately we're not together in person, but we're able to span the globe with this new seminar series launched by IFRR. So Vijay Kumar will be our speaker today, and he'll talk about, it'll be a colloquium focused on aerial robotics, and he will talk in particular about swarms of small flying robots. Let me first say a few words about Vijay. He doesn't really need an introduction. I'm sure all of you know about him and his work already, but just for formality's sake, Vijay is a Nemirovsky Family Dean of Penn Engineering, and he has appointments in several different departments at Penn as well. His group works on creating autonomous ground and aerial robots, designing bio-inspired algorithms for collective behaviors, and on robot swarms. And he's going to share a great sample of his work with us today. His group has won many Best Paper Awards at conferences, and his students and postdocs are leaders in teaching research, business, and entrepreneurship across the globe. He's a fellow of ASME and IEEE, and he's a member of the U.S. National Academy of Engineering. So on top of being a fabulous researcher who's made a great number of contributions, he's also served in so many administrative roles that it blows your mind. He's been the director of the GRASP Lab and took on a number of roles at Penn before now he's a dean. And he also served as an assistant director of robotics and cyber-physical systems at the White House Office of Science and Technology Policy. And that's a huge job, really. So let's go on now and tell you about a new feature that we're going to have today. In order to help us recreate a little bit of the sense of a live in-person lecture, we have a set of panelists whose job, they'll be visible to you, and they'll be able to ask Vijay questions during the presentation, whereas you guys, the rest of the audience, will be asking their questions through Slido. They will be able to ask theirs in person. So here we have a set of people. Felipe Arias is a PhD student at the University of Illinois. Regina Baichi is a professor at UC Berkeley, and Regina is, I think all of us know Regina. I'm really glad she could join us today. Mario Campos is will be here from UFMG at Brazil. Sonia Chernova will be joining us she's an associate professor at Georgia Tech. Maria Polvillo will be joining us from the University of Seville in Spain. Abanti Shama Afros is a PhD student in Italy at the Scuola Superiore Sant'Anna. Gaurav Sokame is a professor and also a dean nowadays at USC. And Deanne Iwachu is a PhD student at Texas A&M University. You will get to see them throughout the presentation. Actually, I have a little bit to say about the logistics before we get started. So Vijay's talk has 3 segments, and we'll pause after each segment and take questions from you. The moderator, who's me, Nancy Amato, will pose questions from the audience that are submitted through this Slido link. So you all should be watching this through the Zoom link, but you can pose questions through that Slido link. And if you got the Zoom link, you have the Slido link too. The panelists, though, are welcome and I would say encouraged to ask questions throughout. So you can also use the Zoom chat, but we're going to primarily be taking the questions from the Slido. Okay, so now I am going to pass over the screen to Vijay and let him take it from here.
Thank you, Nancy. Thank you for that kind introduction. Thank you for IFRR for organizing this. And thanks to all the panelists for joining me and, of course, the audience. We live in a surreal world, and there's nothing better than a robotics session to bring us down to reality, familiar faces, familiar topic. the excitement of robotics research, and I'm grateful that IFRR created this opportunity for all of us. As Nancy said, I'll be giving an overview of some of our recent work, and then pausing briefly for questions, and I welcome comments. A lot of this is sort of new work, and I want to just give you our take on some of the challenges that we have in aerial robotics. Let me first start with some history. Of course, everybody knows that flight started in 1903 with the Wright brothers. But what people ignore is the fact that the early drones had history going back to 1907. So if you look at the gyroplane in 19...
Dr. Kumar, you've muted yourself.
myself. How did I do that? Can you hear me now?
Yes, we can hear you now.
Okay, sorry. I think some Bluetooth device kicked in and started picking up my... So these are some early rotorcrafts. 1907, the first aircraft that took off and climbed up to 2 feet. And on the bottom left, you see the first rotorcraft that took off without any human assistance. And if you're interested, there's a great review article in Wired magazine, 100 years of flight, but through hovering, which is different, of course, from fixed-wing aircraft. So this has been around for a long time, and we first started getting interested in this back. This was late 1990s, and you can see a couple of pictures I show here. I don't show these robots flying because it was really hard to get stable flight, so I don't have good videos. I have embarrassing videos to share with you. But the first robots that really were built to fly indoors, I think Aztec Technologies created the first ones. The Hummingbird, that was our initial work on autonomous flight, of course, done with motion capture cameras. Then a spin-off that came out of our lab, KML Robotics in 2012. So this is a hex rotor aircraft. And so these all had all onboard autonomy, onboard sensing, could fly autonomously. And then 2011, we created the first swarm, if you will, indoor swarm, 20 robots flying in formation in 2011. So a lot of excitement in the research front, but none of us could have anticipated the interest from the commercial front. And so in 2015, I mean, these are all popular magazines featuring drones, and they were everywhere. I think in 2015, for the first time, over 1 million drones were sold in the US by DJI alone. So very exciting time to be working in this area, but as often is the case, exciting technologies are brought down to earth very quickly. And I wanted to show you this picture of the hype cycle, Gartner hype cycle. And this is in 2017, where essentially UAVs, drones, have come off the peak of inflated expectations and descending fast into the trough of disillusionment. And of course, those of you who do machine learning will be gratified to know that deep learning was at the top in 2017. Still at the top in 2018, and if you look at 2019, 2020, they've stopped doing deep learning because deep learning is a cross-cutting technology that's fundamental to everything. But anyway, that's deep learning, but I want to focus on commercial UAVs, drones. And if you fast forward to 2018, it's disappeared. It's now no longer on this hype cycle. But if you look very closely on the bottom left, you will see flying autonomous cars. And this is one thing that the Valley does very successfully. It takes a hard problem, autonomous flight. It takes another hard problem, which is autonomous vehicles that can actually lift into the air, a big mechanical challenge given the power consumption of hovering. And then you combine it, and all of a sudden it becomes tractable. And of course, a lot of money in this business too, starting with Uber and companies like Kitty Hawk. So a lot of excitement continues in this area, but not in what we would call drones. I think it's really had a great impact on research that we do in the labs. So I think there's still a lot of excitement in three-dimensional flight, three-dimensional movement, and the perception, the action, and the fundamental problems that govern autonomy. And I think we're just getting started. The interesting thing to me is that a lot of what industry is doing for the first time is influencing what academia does, but not in the way you might expect. So when industry places an anchor, oftentimes that is a point for young people to say, well, that's where I want to be. I want to solve problems that industry is facing. Another way of looking at it, which is how we look at it, is if industry places an anchor at some point, well, that's where you don't want to be. Because if industry is solving problems in a research area, they throw a lot more resources than academic labs can do. So in both ways, this has kind of influenced the way we think about research. So as we think about where we want to go, the next steps for us is to make things that are smaller, that can navigate indoors in spaces that humans occupy. So obviously safety is a big issue. We think about safety and also think about the smarts that you need. If you're going to be navigating in environments where humans occupy, you want to be able to understand the environment, and all in this very tight, small package. We also focus on speed. As I'll tell you, some of the applications we're interested in require fast response. And then finally, as you make things smaller, there's an inevitable drop-off in performance in terms of what payloads you can carry. So if you have lots of robots collaboratively carrying payloads or collaboratively conducting missions, then you can afford to scale down in size. So we look at how robots can collaborate and form large groups that can cohesively perform as a team and accomplish the mission that large individuals can then also try to accomplish. So we want to operate in environments like this. So very briefly, you look at this very cluttered space, very dynamic space. This is shortly after the earthquake in Nepal. And you'd love first responders to be there and those responders be flying robots. And that's the need for small sizes, and it's also the need for smarts. It's also the need for navigating quickly, which is typically the case in a first response mission. So I want to tell you about work in two areas. First, how we think about fast autonomous flight, and then second, how we think about collaborative work in this context. So let me start with one of the prototypes we built. This was about 2 years ago. So the first thing that you can see in this picture on the top right is a big LiDAR. So this is, at that time, the best LiDAR that was available, a 600-gram vehicle. And for the first time, I realized that when you design vehicles as a mechanical engineer or as an electromechanical systems person, you're designing it around the sensor payload. So it's as though the human body evolved to carry the head and the brain and the eyes, as opposed to all the other things that the human body is capable of doing. So flying with that payload at high speeds meant that you ended up with a system that was almost 3.5 kilos in weight. So not at all small, but again, if you want to lift something like this, given the fact that hovering requires roughly 200 watts per kilo, you quickly scale up in the wrong direction. Likewise, computation. Computation is heavy. An Intel NUC processor weighs, with all the heat sinks and everything, weighs another 200 grams. So that was all driving us in the wrong direction. But I want to tell you about some of the work we did with these initial prototypes. Before I tell you that, one of the things we did was to see, well, can we actually reduce the size of the payload by going to 2D LiDARs? Well, 2D LiDARs meant that you had to actually add a nodding axis. So we had a LiDAR which could nod up and down to create a locally 3D map, and also a camera IMU system, which we essentially used for visual odometry. So everything you see in this picture was driven by these sensors. There was no GPS. And essentially, you have to understand the environment. I'm showing you a very, very simple cartoon on the right side, a 2014 cartoon that shows the planar version of what we have to do. You're getting a bunch of laser scans. You're quickly trying to segment the environment into occupied space and unoccupied space. And you're trying to plan a trajectory, which if you see on the top left, is an optimal trajectory It minimizes a performance function that is based on time, and it's based on a measure of smoothness. So J is measuring the smoothness of the trajectory. The smoother the trajectory, the better your perception problem becomes, the less the issues you have to deal with as you lose track of features. And at the same time, the dynamics is also favorable for the vehicle. And the more you tune up rho, the more important time becomes and the faster the trajectory becomes. Now, this system is a nonlinear system, but with some clever transformations, you can reduce it to a linear system. The hard part is really thinking about the control space, which is always, it's not convex. It depends on the constraints that you have on your inputs. And of course, the underlying space, the free space, which is also not convex. And thinking about the system, it ends up being a fourth degree system with input and state constraints. It's non-convex in configuration space, as I've just told you. And a lot of the initial work we had to do was think about how to plan these motions in these safe corridors. And one key thing here is that these corridors lie in different homotopy classes or homology classes. So reasoning about trajectories that go left around an obstacle versus right around the obstacle. And all of this you have to do in real time with a limited field of view. So, typically you have a LiDAR, let's say like a Hokoyu, you have a 20 to 30 meter range, which really means that you have to plan motions in that field of view, and you have to scale back the velocities so that at the end of your field of view, if you encounter, let's say, a brick wall, you know that you have to come to a stop. So you essentially have to figure out how the field of view constraints play into your dynamics. And all of that needs to go into this motion planner. What I wanted to do is to just show you an example of some flights that we were able to do. So this is this was funded by DARPA. The goal is to go roughly, in this particular case, these tests were roughly 300 to 500 meters away. Go find an object of interest. We're not going to tell you anything about the environment. Come back and tell us what object you found and where. So I'm going to play this video, and the robot's going to take off. Its local representation is in the bottom left. What the robot sees is on the top left, and the final results are overlaid on a Google Earth image on the right side. So when I play this video, you'll see the robot take off. You'll see the initial map being formed on the bottom left. And the box essentially tells you the field of view of what the LiDAR sees. Not a whole lot, right? And you're trying to reason about free space. The max speed in this case is about 5 meters per second, and it's governed primarily by the sensor we carry. The better the sensor, the faster we can go. So it's not a mechanical design constraint. It's really a constraint of how far out you can see. You'll see it find ways around the trees. And now keep in mind, the perception system is very dumb. It doesn't identify what it sees. It's just trying to distinguish between free space and occupied space. So when it gets roughly to the point it needs to go to, it encounters this building. And it tries to find a path using this optimal control algorithm, but staying inside the free space. And it's actually a very poor search strategy because it's all very, very local. It has no global knowledge of the environment. And as it turns the corner, you'll see that it finds an opening. And as it goes in, it hurriedly has to change the contrast of the bright Florida sun outside to the dimly lit interior of this building. The exposure control is again tuned to the illumination. It goes around still looking for this object of interest. Happens to be a red barrel. Once it finds the red barrel, it says, okay, I found it. This is the approximate location. It turns back and gets back to where it started to report, hey, this is the red barrel I found, and this is where I found it. All of the position estimates and velocity estimates are derived from these pair of stereo cameras and an IMU. There is no GPS. There is no radio control. The operator can only hit go and then has to watch. This is a mission with surprising complexity, but what is impressive about this is we were able to do this trial after trial in these kinds of settings. Again, Nothing too complicated in the sense that the area is not too cluttered. But if the area were cluttered, it would come to a stop. It would basically say, I cannot find a path. But mission after mission, it was able to run successfully without crashing into anything. What's the knock against this? The big knock against this is that you're carrying a LiDAR package. Because of that, you're heavy, and because of that, you can't really travel fast. So since this experiment, we started building smaller vehicles. So what you see on the left side is something which is about 3.5 times smaller. This is a 1 kilo quad rotor, powered entirely by cameras. Now, it does have a 3D time-of-flight camera with a 6-meter range, but bulk of the processing is done based on the stereo camera on board. You could see navigation now in much more cluttered environments on the right side. My colleague CJ Taylor did a lot of the work on real-time dense 3D depth estimation, which powered the perception system here. You could see the speeds are much slower, about 1 meter per second to max 2 meters per second. But this time it's limited by the 3D camera. Once again, range is limiting how fast you can go. In the previous case, it was the range, but it was also a combination of the inertia. The bigger the platform, the more time it takes to slow down. Here, it's primarily the range of the system. So in both cases, the navigation strategy is local. We're only interested in building a local map. We can presumably always reconstruct a dense map, a fancy map, once you return to base. But if you want to drive really fast, all the computational resources, and not a whole heck of a lot of computation on board, are being dedicated to figuring out what is free space, what is not, and how to navigate as quickly as possible in the general direction that you've been commanded. So this is lightweight autonomy, and we've gotten even smaller now. So this is a 250-gram quad rotor, and this is where what industry has been working on has benefited us. So the payload you see on board is roughly the payload that you have on your smartphone. An Android phone has essentially the same Snapdragon board that this is using. It also has 2 cameras. Again, your Android phones probably have 2 cameras. It has a 4K camera, which we don't use at this point. But essentially, again, all the estimation in terms of positions, velocities, orientations are done by the stereo camera and the onboard IMU. It works indoors, it works outdoors, again, not relying on GPS. And if necessary, you can use the inbuilt cell modem for alternative communications. So once again, you see this preliminary swarm we built, which again is working based on the stereo cameras and then communication. In this case, we have a star-shaped communication technology, which we have since relaxed. But the ability to form patterns, not very complicated patterns, through single commands, which an operator can issue through a Wi-Fi link. So this video goes on. The one thing later on, if I played it long enough, you will see it operating in dimly lit environments. Nothing that we've accomplished. It's just a sign of how the smartphone technology has matured, how the cameras that you get at the price to performance ratio that people expect in a smartphone is really more than adequate for robot navigation. So this is what I was alluding to earlier. So as we scale things down, and we've even tried to make it even smaller, and this time it's based on the simple realization, as you see on the bottom left, if you scale down the inertia of the system, if you collide with another robot or with the environment, as you'll see in some of these videos, the impact that you suffer, the change in momentum, is actually modest. And because of that, you can recover from that. So again, an interesting way in which robot design is actually based on your knowledge of mechanics, and as I'll show you in a minute, also based on how you sense the environment. So if you look at the bottom, you'll see the exact same robots. Now these are 133 grams, not using a Vicon motion capture or anything like that, using just onboard cameras, but now colliding with the environment, and we're detecting collisions based on the IMU and based on cameras. We don't think about it, but when we collide with the environment, obviously our eyes feel it. We don't think about our eyes because every other part of our body probably feels this too. But using a combination of IMU measurements and vision, you can not only detect collisions, but you can also recover from these collisions. So this is an important part as you try to scale things down. You get into more complex environments. And the reason you want to think about collisions is because as your cameras become smaller and smaller, your processors become smaller and smaller, things get a lot noisier, and your information about what you see in the environment gets more and more, shall I say, poorer quality. And so collisions are inevitable. And I think this idea that you build small vehicles that can recover from collisions, I think is a very promising research area, particularly as you think about robots in environments that humans can occupy and are intrinsically safe. Let me stop here to see if there are any questions, and I'll hand it over to Nancy and the panelists before I get into the next thing I wanted to talk about, which is on robot swarms.
Do we have anyone from our panel who would like to pose a question? Remember, if you do, you'll need to unmute yourself.
Sure, Nancy, I'm happy to ask a question. This is Gaurav.
Go for it.
So Vijay, this is a really exciting evolution of platforms that you've sketched. I'm wondering whether, I was struck by the comment you made, which is that developments in sensing have led the way typically for much of the work we do in robotics. These sensors tend to come first. We find ways to bolt them onto a chassis. That sort of governs what the chassis has to look like because you work with the sensors you have, and then the cycle repeats, right? Do you think this will change over time where the sensing will plateau at some point and we are headed for a reversal of this situation? Or do you think this trend is likely to continue and we can at least, if we can't ride the hype cycle for everything, can we at least ride the hype cycle for sensing a little while longer?
I think if you want to build autonomous machines, there are two things that you have to look at: perception and action. And I know Rujna is in the audience. She can tell us everything about that because she was there at ground zero. But a philosophical debate we can have is what is harder, perception or action? And I believe the answer is perception. It's interesting, you have this conversation with the perception expert and the person will say, well, it's action, obviously. But no, I do think it's perception. I think understanding the 3D world, especially at high speeds, is a big challenge. So even if you go back to the 1990s and you ask what made mobile robots successful, I would argue it was the initial laser scanners, the fact that we were able to pull it out of industry, out of the shop floor and bring it onto mobile robots. And that's why our earlier mobile robots were all clunky, they were all ugly. And over time, we've figured out how to make them work with cameras. So I think up to a point, it's sensing that's going to drive the evolution, but not necessarily sensors. And this is where I think modern techniques in computer vision, I think, show a lot of promise. So it may be that you will be able to extract more and more out of a piece of silicon than you used to be able to. And again, it has something to do with processing as well. So it's an interesting question, Gaurav. And I think looking at industry, where industry is going, can help us sort of roadmap our way to faster and more capable autonomous machines.
So Vijay, I wonder if you stop sharing momentarily, then we could get more of our panelists on the screen during this Q&A time. Yeah, great. Regina.
Yes. I was wondering, music to my ear, all what you said, but I was wondering on those legs that you stand on, have you guys considered to put springs as a measure of hardness of the surface where you land? This might be very simple and useful in some ways, spring stiffness estimator.
Yeah, no, it's a great question. Our initial, when we built these shells to protect the robot, our initial shells were all compliant. But when you make them compliant, there's mechanical resonance that unless you have a sophisticated brain, you cannot compensate for. So we were led into this rigid design because the rigid design allows you to think about contact as a binary problem.
Yeah.
Right. So it's interesting as an engineer, the obvious solution is to come up with something compliant, and anybody who does physical human-robot interaction will tell you that. But not if you really want to minimally infer the state of the world.
Right.
Sorry, infer the state of the world with a minimal sensor package.
Yes. Yes.
Yeah.
Thank you.
I was wondering, can I ask a question?
Yes, go
Nancy is
for
the
it.
boss.
Yes,
Okay.
go for it.
So I was wondering, the last one where there were the 250 gram copters, was the localization, was it connecting with the central system, or was the path planning was done only locally based?
Avanti, great question. So yeah, so everything has to be done locally. I think, I mean, you know, we have all these paradigms of self-driving cars that there will be somebody in the cloud that'll come out and bail you out. And no, when we build robots, all the safety loops have to be on board. So all the path planning is done locally. The estimation has to be done locally. Yeah, absolutely. I didn't talk about this, but our goal is to send these little robots someday into nuclear reactors where there will be no human contact and there is no radioactive communication with the robot. So it has to be fully autonomous. Yeah.
We
Okay.
do have, go for it. Go,
Sorry.
Mario.
Just another quick question regarding the experiments. Are they sharing any information when you have multiple drones?
Yes. Hey, Felipe, can I defer that talk for the second piece where I do want to talk about communication?
Sure.
Yeah.
So Mario, it looked like you had a question. You're muted, I think. I don't hear him. Does anyone hear him?
Nope.
No, we're not hearing you, Mario. We can't, now you're actually muted.
Okay.
He had trouble with his camera at first too. So Maria, it looks like you may have a question.
Yes, related to the perception of the environment. When you have multiple drones, how does it affect to the swarm that one or two robots face during the execution of the task?
Maria, may I answer your question the same way I answered Felipe's? I'm going to talk about this next, the multi-drone problem, and I'll tell you what some of the challenges we're facing are.
Everyone should take a good cue as to how VJ, very elegantly postpones these in a nice way. But you can remember them if you want, if he doesn't respond to them later. Deanne, I think you had a question. Go for it.
I had a small question about the robustness to collisions. Is it also dependent on the speed of these robots?
Yeah, absolutely, Deanne. So in general, it depends on the mass times velocity, right? So if you make the mass smaller, you can sustain collisions at higher speeds, right? And it's true for humans. When you play sports, I mean, the smaller, lighter people tend to be less injury prone than so in American football, you have these big behemoths, and when they collide with people, you have serious injuries, right? So that's the intuition. And it certainly works out in 3D flight. It's even more so because there is no ground to kind of support you. There are no reaction forces.
So we do have a couple questions that came from the audience. One was, how important is the role of synthetic imagery data for training these navigation systems? And do you have any particular recommendations for simulation tools?
Yeah, so again, may I defer this one?
Yes, you may. We'll
So
remember it.
one of the things, yeah, so let me do that, and I'll come back
Sure.
and tell you how we're using that for, but everything I showed you thus far is, I want to hasten that this is all model-based. So everything that you see, yes, there's a little bit of adaptation a little bit of learning in the sense of tuning the adaptive control loops and so on. But there is no synthetic imagery being used for training anything. Only thing is for object detection, which is kind of trivial here. This is not really a big advance. But in what I'm going to be telling you next, when you think about drones looking at each other, and it's not only a question of detecting, but also a question of localizing and then tracking, some of these frameworks then become important.
So we have a couple questions that came in that I think are related more to this first segment of your talk that I will maybe bring up together, and you can decide how you want to respond to them. But I was really struck by when you made the remark that the human body evolved to carry around our main sensor.
I didn't say that. I said if. Imagine
okay.
if the human body had evolved just to carry the head around. And that's a good hypothesis, by the way. The head is the most important part of our body, I think.
Well, still, it was that's going to stick with me, and I think that these questions are kind of asking around these kind of platform issues. So, does basically your rule of thumb, your 200 watts per kilogram rule of thumb, hold as you move from a 2 kilogram platform to a 133 gram one when you move down? When do we hit the floor on realistic quad rotor scaling? And then another question is, for the fast maneuvers, is the bottleneck from the sensor range or onboard computation? Oh, and another one popped up, but with the sensors getting smaller and more intelligent, is it reasonable to have a swarm of highly capable units? How would that enhance the overall performance?
Yeah, so great question. So the 200 watt per kilo number is based on experiments we did from 25 grams all the way up to 2 kilos. So that's a rough rule of thumb. Keep in mind, if our lives depended on designing more efficient quadrotors, we would probably do that, and we might eke out better efficiencies. So I know for a fact that there's one startup in the Valley that actually claims something closer to 100 watts per kilo. So I'm not saying that's not possible, but that's a rough rule of thumb that you'll have to deal with. When you get to larger aircraft, you get some scaling benefits. So that's why helicopters are actually much, much more efficient than quadrotors are. But hovering is inherently an inefficient problem. The other question that was asked, to me, sensing and computation, if you think about perception, sensing and computation go hand in hand. So you can compensate for weak sensors by more computation, at a very high level. But sensing range fundamentally limits how fast you can go. I mean, if you drive at night, your night vision, most often your night vision determines the maximum speed you're at. It's not how fast you can process things, and it also has to do with how big a car you're driving. If you're driving a big truck, chances are you'll be a little more careful than if you're driving a motorbike. So I do think those two things go hand in hand. So the sensor field of view and the mechanics, and of course computation plays a role. But to the first order, I think it's not computation in this case.
Cool. Should we move on maybe and let you give your next component of your talk?
Sure. And I will run through this relatively quickly. I know we've spent quite a bit of time here. So what I want to do is to talk a little bit about what I believe the fundamental issues are in terms of swarming, which is to design not only perception action loops, but also perception action communication loops. And if I switch to a very simple problem, which is how do you fly information using perception action and communication? Rujna, I feel terrible talking about this in front of you, but I'm gonna go back to the 80s and imagine I was a graduate student listening to Rujna, and this is what she taught us. So obviously, perception informs action. Your observations inform what actions you take, but there's the opposite flip side, which of course is the paradigm of active perception, which Rujna formulated, which is you want to move for better observations. So this idea has been around for 30 plus years. I think the real question is, how does communication fit in when you go to multi-vehicle teams? So communication also impacts perception. So if you have communication, we can share observations, and we can also communicate to coordinate better observations, right? So this is the idea of perhaps active communication. And of course, communication informs action. And then if you want to move closer to somebody you need to talk to, you can communicate better. So it's an interesting set of feedback loops. And if you really want to study swarms, you have to unify not just perception action, but also perception action and communication. And of course, a lot of it depends on the task. I'll be upfront of that. But this turns out to do it even for a specific task turns out to be harder than you might think. But let me tell you what we know how to do, and then I'll tell you what we don't know how to do. So again, I'm back to cameras. Why? Because it's the only lightweight, low power solution. So what you see here is 3 drones, one of them localizing the other 2 drones. So this is a very lightweight network that's been trained. I'll say a little bit more about the network soon, to detect drones. And we use a probabilistic estimation probabilistic approach to estimating the joint state. So here you have to remember that every drone sees every other drone, but may not be able to identify the drone. So there's a data association problem to start off with. Second, every drone might not see every other drone, and if it does see it, there's a finite probability of a false detection. So you have to factor all of these in as you think about your big state vector, which includes robot I's position in robot J's frame, robot I's bearing in robot J's frame, and robot I's yaw in robot J's frame. And then you want to translate all of that to a common reference frame that doesn't exist, which means you have to do consensus on what the common reference frame is. So, so this is how we think about formation flight. And of course, we want to do it only with cameras and IMUs with our 250 gram platform. So this is what we're working on. This is where we use synthetic imagery. So if you want to train neural networks for semantic segmentation, so here the segmentation is pretty trivial, drone background. The problem is that in computer vision, a lot of this stuff has been done with large, rich data sets. In reality, the world of people that are interested in small drones and drone-to-drone detection is very, very small. And so the number of data sets you can find in small drones with different orientations at different ranges and cluttered background is very, very, very small. So we're generating this ourselves. And what makes it even harder is that you're dealing with these small platforms, size, weight, and payload constrained platforms. So here we actually do, T. Nguyen, the first author in this paper, has actually started assembling a set of synthetic data sets where essentially he takes real world drone images captured in different settings, but superimposes it in different backgrounds, in different video settings, and uses that to train the networks with surprising success. So that's the one question that was asked before. But other than that, this is just a straightforward detection problem. The only thing is we take into account false positives and false negatives into our probabilistic formulation. So this is the MAVNet we've designed. So remember, everything has to operate on board, and we just have a small inference engine. It's a TX2. We also have an FPGA on board, but that FPGA does mostly low-level processing, all the detecting corners and detecting edges and so on, and mostly used for stereo visual odometry. But so the TX2 has to run this engine, and so this is our ground truth. This is our inference engine running, and we want to run it at least at 10 frames a second. So you could see in the table, we're able to get to about 19 frames a second with reasonable performance with our MAVNet. And of course, there are many networks that do this. The only difference is we're trying to do this at a very, very small payload. So then comes the question of communication. And this is where communication loops are extremely hard to model. So to figure out what a robot needs to tell another robot to do feedback loops, and to figure out what a robot needs to do once it's heard some salient information, turns out to be remarkably hard. Yes, there are model-based control methodologies, but what I want to show you is that if you use that insight that you get from model-based control and you design networks that learn, you can get much better performance. So I want to take a very simple example. But first, let me just tell you the framework we use. So the framework we use is, so the question we want to ask is, how do you formulate actions based on what you've heard? So the idea is very simple, right? You have a graph of robots, and you want to aggregate at every node information from neighboring nodes. And then you want to aggregate that and figure out what that information means. So the idea that you're doing this is captured inside what are called graph neural networks, which are very similar to CNNs. So CNNs, of course, come from mostly from the observation that you oftentimes have pixels or nodes that are arranged in a rectangular grid. And this idea of aggregation information at each node from neighboring nodes is just very natural. So in robot systems, it's like a CNN, except these robots are all over the place. The graphs are similar in the sense that they're driven by proximity relationships, but not necessarily because of wired connections. So these GNNs are driven by edges, and the edges are based on who sees who and who can talk to who. So each of these edges represents an information link in that sense. So rather than think about what a single robot does and what its belief state is, I have robots talk to immediate neighbors. So here k = 1 neighbors. Look at their belief states through communication as available, and then average over that. And if necessary, I can go to k = 2 or k = 3 and so on. And eventually, if I have enough bandwidth, I can talk to all my neighbors through multi-hop networks and then aggregate this information. So a lot of this work has been inspired by collaborations with my colleague Alejandro Ribeiro, who's a signal processing person, and so he thinks of this in terms of signal processing on graphs, and we think of it in terms of control systems on graphs. So at the end of the day, you're doing convolutions. It's a big filter, but the filter is now based on belief states of agents, and each agent can run a perception action loop locally. So that's the key idea. And there are properties of GNNs, which you also see in CNNs, one being this notion of permutation covariance. If the graphs are similar, the outputs will be similar, right? So you can renumber the graphs, you can renumber the inputs, the outputs will be the same. The other thing is sort of this property on graphs, which is you perturb things a little bit, and hopefully you get a small perturbation in the outputs. So if you change the graph a little bit as the robots move and you've got a dramatically different output, that would be a problem. Well, GNNs have these two important properties that kind of lend themselves to swarming and flocking. So I want to show you our first result. And so my colleagues at Penn, George Pappas and Ali Jadbabai, who's now at MIT, and Bert Tanner, who was a postdoc that was working with George and me, wrote this very interesting paper. They basically showed something that Boyd had empirically demonstrated using computer simulations, which is if you get robots to look at their nearest neighbors, and if you get them to stay close to the nearest neighbors while avoiding collisions, while having a force that kind of tries to align themselves, the robots will eventually align themselves. So this paper by Tanner et al. Shows that is a control law that essentially looks at an input that averages over differences in velocities and differences in positions modulated by a nonlinear term, a potential function, will guarantee that these robots will eventually flock. And what this paper shows is the theoretical proofs, but what they don't show you is how you derive the set of initial conditions from which this algorithm is guaranteed to work. Yes, there is a set of initial conditions with certificates, but to get initial configurations and velocities that satisfy that certificate is really, really hard. So for example, I show you these blue configurations, where these robots are amazingly close to each other with velocities pointing in different directions. And if you use their algorithm and let it play out, you'll find that they diverge. So perception, action, communication loops working based on top eminent control theorists, but not able to predict when the algorithm breaks, right? So we set ourselves this challenge, and by the way, I'm not dissing George, who was involved in this collaboration. We recognize that model-based control is limited in performance. Great for intuition, great for proofs, but actually not so great in terms of going outside our comfort zone. And so we said we want to try to train a graph neural network to imitate what we know from control theory. So the idea is that you essentially train this network and you have a self-supervised training, except it's not really self-supervision. We have an oracle that essentially assumes that I know what the centralized controller will do, and it tries to imitate this centralized control policy. Now, this assumes I know how to do centralized control, which I can only do for very, very small units. But using that, you could see that on the left, the model-based controller fails, only because I picked initial conditions that were unfair to the model-based controller, while the learned controller performs well. So the learned controller performs almost as well, in fact, sometimes better in conditions which satisfy the model-based control assumptions, but perform much better in cases where you go outside this envelope. So that was the first observation. The second observation, and I'm going to skip this, this just shows more of the same. The second observation is that if you train GNNs on small numbers of robots, you can actually extend them to large numbers of robots. Why? Because graphs locally look very similar. So if I look at a proximity graph of let's say, 100 people in a bar, wait a minute, we shouldn't be talking about bars today, gathering in socially distant spaces, if I look at the proximity graph, locally these graphs will look very similar. And so what you see on the left and on the right is just the same thing on a fancier simulation. Our ability to train robots to go to formations based, again, on a centralized reward function that's only based on local information. Local information means I only look at small teams. Small teams means I can actually solve the problem centrally. I don't have to worry about the fact the problem is NP-hard or anything like that, or intractable. I can actually brute force it. So that brute force oracle trains this more complex system with performance that you see in these videos. So again, two ideas. One is you use your intuition from whatever models you have. Second, you don't think about large robot problems, you think about small robot problems, and you brute force the small robot problem to train the large robot problem with performance that you cannot get otherwise. So those are the sort of two take-home messages. And I just want to show you another example. This is a perimeter defense problem, which many people work in the context of pursuit evasion. A bunch of defenders trying to prevent a bunch of attackers from entering the safe zone. The red attackers, the blue defenders are trying to intercept them. A very hard problem to solve if you go beyond 1v1 or 2v1. But if you go to 5v5, you might be able to brute force it. There's no way you're going to solve it for 15v15. And what you see on in this video is essentially our ability to solve this problem through these learned policies. And in a minute, you'll see our ability to solve these with limited fields of view as well. And so the interesting thing when you have limited fields of view is that information is very local. But again, you have to train this using the centralized policies, and it does a surprisingly good job of intercepting the attacking intruders. let me pause here. I do want to talk about a couple of applications, but I do want to answer questions before I do that.
Well, actually, I'm wondering if we should let you talk about this because
Okay.
we, technically just have a few minutes left.
Okay,
And
let me do that. So I want to talk about applications and tell you why I made a comment about industry, and I want to tell you about some of the startup companies that I started working with. And so I'm convinced now that these companies can solve the problems we're trying to solve much faster, much better. So one of them is Exyn Technologies. A lot of former PhD students, postdocs, and master's students from my group have joined this company. It's now 30 strong. The thing they do, which I find is just remarkable, is take everything that I've described, but now running on a platform that they now sell to mining operators. So this is in a gold mine in Bulgaria. You can see this robot. The LiDAR is spinning because you want total 360 information, creating maps of these stopes. So these stopes are big vertical chimneys, if you will, in mines connecting different strata. Again, things you cannot do through teleoperation. There is no radio link that will go that far. And humans cannot build scaffolds in every stope, in every mine. It's a very dangerous operation. And you'll also find that these environments are very dusty and not suitable for humans. And so they do it with a remarkable precision and the kind of reliability that you expect in an industrial prototype. So this is exploration, again, doing loop closure in a salt mine. This one happens to be in Utah. A lot of this, however, is LiDAR-based. Very little computer vision is used here, except for semantic labeling of objects. When you're underground, there is no illumination, and so cameras fail us at this juncture. The other thing I'll mention is if you're in the drone business and you're worried about government legislations and regulation, nobody is going to bother you if you're 10,000 feet below the ground. So it's one area where the FAA and other regulatory agencies don't really care. So companies actually found a very interesting niche market. But also the same thing in the kinds of environments I was talking about. So not quite 5 meters per second speed. So this is, I think, well, this video is about 2x, but you'll see an abandoned building, real-time mapping, although the map I'm showing you was reconstructed after the fact. Much of the mapping is primarily LiDAR-based, but you'll see it build a map of this building and then go inside the building, build a multi-floor three-dimensional map. What you're seeing in the inset is really the trajectory being displayed in the post-process map. But the map is being built in real time for obstacle avoidance. And you'll see a little bit of computer vision here with cameras as they detect humans. The only thing they're capable of detecting here is just humans, because they back off. Whenever they say human beings, they back off. So just some very, very simple object detection. And so these are things that we've stopped doing. So why don't we use LiDARs for 3D mapping and so on? Well, industry's already there. There's no point competing with industry. Another area where we've used cameras extensively for autonomous navigation is in orchards, where our primary goal is to do yield estimation. We count trees, we count forests, we count fruit. Again, some of our early work on obstacle avoidance, going through forest canopies. This was done 3 years ago. It's matured quite a bit. Fast flight. But what we're doing now is really detecting objects, tracking those objects, and then estimating 3D structures. And the interesting thing here is that detecting objects, identifying the semantics of objects has also taught us to build better localization algorithms. So very simple, if you navigate in orchards, you get lots of features, most of them from leaves. Leaves don't offer reliable features. So really a bad thing to do would be to track leaves and say, I'm going to do visual odometry and mapping based on that. But if you detect fruit or tree trunks, that's great. And so tagging objects allows us to essentially build better maps and three-dimensional maps, as you can see here. Lastly, I just want to conclude. I think one thing to me, with all this interest now in on energy and sustainability, And all these announcements that are being made, you see Amazon, you see Google, you see Facebook, everybody wants to save the environment. But one very simple question, if you ask, how much carbon do we have in the world? How many trees do we have in the world? How much timber is there in the world? Nobody knows the answer. And I show here an overlay of all the forests in the world. Obviously, Mario, where you're in Brazil, a lot of forests in the US. I was starting to find that in India, there are no forests because everything has been cut down. Africa, there's a lot of forests. So imagine being able to map all the forests, right? And so today, how do timber industry measure how much carbon they have? They literally walk around, they hand collect the data, and they hand collect the data by measuring what is called BDH, DBH, diameter at breast height. So they have a measuring tape, they go around the tree, they do spot checks, and they extrapolate over entire forests. There are parts of the forest they've never visited, and that's how they have these estimates. Of course, these estimates are very bad. And so from fruit, we've also started thinking about a forest, and this is another startup, Trifo, that's doing this work. And it's just striking that in the 20th century, all of a sudden you're coming out of all these new announcements, Shell, Microsoft, Blackstone, we're going to rethink climate. It took them a long time to figure this out, and particularly with COVID-19 has put the spotlight on these issues and put them in sharp focus. But ultimately, at the end of the day, if you have to take actions about the environment, you need data. And I think robotics can play a huge role. I know, Gaurav, you've done work underwater, dearth of data there. But on land, I think there's a lot we can do, and that's where I think drones can be very useful. Let me stop here. I'm going to just flash a picture of all my students and some former students who have helped in the work. Maybe I'll stop screen sharing so I can see the panelists and you, Nancy, and take questions.
Well, thank you, Vijay. That was, fabulous, actually, really exciting. Who wants to start off with a question now?
I can do it.
Sure.
So Vijay, I really like this diagram that you showed at the beginning of the second session, the one with the sensing, acting, communication, and the arrows showing the relationship between them. And I was also thinking about how for people outside the area, if they've seen the Olympics demo, if they've seen some of the videos you just showed, the field almost looks solved, right? You see these amazing demos, and it's like, well, what is there else? What's left to do? And I think that diagram was really, really elegant at showing how much is left. And I was curious about your input, because you showed all these arrows of how everything is interconnected, but we don't have a system that can do all those things at once. That seems like the holy grail, right, for researchers today, is how could you trade off active perception with action for communication with all these other arrows. So, to me, that was a really interesting way to think about what's left in the field. And the fact that the demos we're seeing are incredible, absolutely incredible, but are only addressing a very small subset of that, and that the rest of the picture is still sort of left to be solved. Is that right?
Guilty as charged. Yeah. If I suggested that we've solved all the problems, no. You're absolutely right. This is a framework for thinking about multi-robot systems. And I claim this is the only way to do it, right? So just like, perception and action, we have to go back and forth between both those things to solve many fundamental problems. I think now you're just complicating it by adding communication. But that's, I believe, the right framework. So you're absolutely right. It's a philosophy when you approach these problems.
And you didn't say it was solved. I think the perception of seeing such a cool demo, many cool demos, is that one could start to think that. But I think there's plenty of work for young students in the audience to think about in this context.
I'm glad you emphasized that.
Who would like to go next? Regina. Oh, there you go.
Yeah, thank you. just want to remind everybody that we have some very well-known and accomplished audience, like Takeo Kanada is on the
Well,
net.
I'm
Yes.
glad you told me now. I would have been really nervous if I'd known before.
And also Mark Kutkowski and several others. But any case, what it tells, so here is something that hasn't been brought out, and I like to, give an emphasis to what Sonia was asking. The perception action, the biggest challenge, and still it is what is the minimum information you have to take from about the environment in order to safely and competently carry out the action. You don't have the time to just take all this data and do 12-hour processing. You have to be very selective. Now, the communication adds another dimension to this real time. What is your channel that you can send the collected data, and what is the minimum and or maybe not minimum, but absolutely necessary information you have to communicate to the other partners so that they can be useful, helpful, and so forth. So this really, to my mind, brings in, especially this situation now we are in, that we are Zooming, at least I am Zooming every day from 9 o'clock until 2 or 3 o'clock, communicating with different people. And since I just retired, so I'm not teaching, Shankar Shastri is teaching the course, but I'm still very deeply concerned, how are we going to teach through robotics the sense of the forces, the contact, stiffness, and all the physical properties through the visual communication. So I'm actually thinking very seriously about developing something cheap that can give tactile perception to the students, because I'm seriously concerned that in 1 year we are going to have a generation that didn't develop these physical properties.
You're absolutely right, but I do think that so I am actually helping a high school student who is 3D. He's got a 3D printer at home. He's building his own arm, and he has a little Arduino controller. And I mean, in no other world would I have the time to interact with this kid. Because this kid, first thing he would have said is, "Can I come in your lab?" And I said, "No, I don't have any room for you." But the kid was persistent, and he said, "Well, this is what I built," and he caught my attention, and now I'm actually working with this kid. So I do think every time you have a crisis like this, there are new opportunities.
DJ, it is true, but we shouldn't forget all those kids who don't have those
exactly
access.
Exactly. So to me, that's the thing I worry about, the kids that don't. I mean, the students we teach that don't have access to proper internet. Even if they have access to internet, they don't have a home where they can study quietly. So I think as we think about all of this, and I think even in a pre-COVID-19 world, robotics has been guilty of sort of ignoring this divide, and perhaps even exaggerating the divide. So I think you're totally right. But I do think as educators, and yes, we don't teach that. Many of us don't teach the truly disadvantaged kids. We do have opportunities to innovate, and
so communication will be important.
Yes. Yeah. And knowing what to communicate will be even more important.
So Mario, I don't know if you got your mic working.
Let's see if it works. Can you hear me?
It works, yes. You can.
Okay, great. Yeah, I had a small problem here. Also, there was a great talk, sequence of talks. A quick question concerning to something that's I think is relevant, of course, energy, right? We have all these little devices flying around, and you have the energy problem, right? Because we have to balance and optimize as far as communication sense is concerned, of course, motion. And how to optimize this global in the sense when you consider, first, logistically speaking. If you're thinking about the Amazon forest, for instance, as you mentioned, if you want to do some kind of sensing, to perform some measurements of the trees there, right? So how you deal with the logistics with respect to that?
This is a practical question, and drones, even a 30-minute flight time, cannot put a dent in that problem. So the way it's done in forests in the US is that there's somebody driving around in a truck, stopping and making measurements. So you could imagine that that person is still stopping to do spot checks, but every time the person stops, there's a fleet of drones that take off from the back and go in 3 different directions or 5 different directions. And they do a really rich data set collection. And so there would still be spot checks, but the spot checks would be over large areas. So to me, that would be the big difference. And then in the Amazon setting, I think you definitely need to do this from the air. But again, how much carbon is there on the Amazon? Most estimates, at least to my understanding, are derived from aerial imagery, not from below the canopy footage.
Exactly, because the canopy basically it's kind of entangled together, so
Yes.
it's very hard for you to see below it. So
yes.
or beneath it.
We have a couple questions that we didn't come to yet that had been submitted. I can there's a few of them that I think can fit together. One is, when you say perception is harder than action, where do you see the role of modeling what you perceive? How you perceive affects how hard it is to act. And another kind of more practical perception question maybe is, regarding the perception constraint, is there any mathematical relation of field of vision, perception delay, and maximum speed that the drone should go?
I'm not sure I understood the first question. The second one, absolutely, right? So delays will, that's one thing we know how to model. How do you model? So it's a feedback loop. If you know what the dynamics is, you know what the time delays are, you can actually figure out how fast you can move. So that part is reasonably well understood, I would say. But in terms of the mathematical modeling, I just said that what we know today about perception is, I think, much less than what we know about action. I'm saying this qualitatively, in the sense, if you want to build an autonomous system, if I just look at the amount of stuff I need to learn about perception, it's just a lot more than what I have to learn about action. It's a qualitative, very qualitative statement.
Okay.
Yeah.
Daniela actually posted a question in the Zoom chat.
Yeah, I saw that.
Did you see that?
Yeah.
I don't know if everyone can see it. I think not. So we should read it. Vijay, I was struck by your comment about things that are better done in companies. Can you comment further on what problems you think could be done by companies and what are the opportunities for academia?
Yeah, so this is, I always get into trouble when I say this, and I've had arguments with people, but a lot of robotics problems are systems problems. And if industry is interested in a systems problem, they will throw a lot more resources. And I would argue that your smartest student, no matter how smart he or she is, will not be able to compete with big industry. So that was my general comment. So in some sense, if you know industry is going in a certain direction, it probably means that that technology is maturing and there are system solutions for that problem. Would you recruit a new PhD student and ask him or her to spend 5 years on that problem? I don't think it's fair. So that's what I meant. And so in some sense, what we think about are problems that are likely to be important 10 years from now, maybe 20 years from now. If it's not important, it doesn't matter as long as there's an intellectual challenge. And so at least in our lab, these are some of the principles we use. So when students come to you and say they want to work on something because Google is working on it, that probably is the wrong logic, right? And that's really what I meant. So in aerial robotics in 2011, 2012, I could have done whatever I wanted. But now to compete on things that DJI is working on, or SkyDO, which is a amazing company, would not make sense for me.
Sounds good. Anyone on the panel have a question, comment? Maria.
I would like to know, for example, during the experiment, doing mapping and localization, you have some ground truth or reference to know what is the precision of the map or the localization?
No, it's all relative. After the fact, we can do the ground truthing, but there is no a priori coordinate system, particularly in swarms. So by consensus, you have to say, well, robot 1, the starting position of robot 1 is the global coordinate system. If you do it either by consensus or you do it by fiat, and you say that's the global coordinate system. So I think this is a big problem. I think in the indoor robotics field, I think many people have done this. A lot of map merging work going back at least 10, 15 years, I would say. But in doing it in the air with sensors that are not great, and doing it with short flight times is actually pretty tricky. And so if you assume that, and by the way, robots are also not very reliable. So, and I could go on and on about ROS requiring a master and how difficult that it is to deploy that. So you really have to be completely decentralized and not assume that you have a global coordinate system at all.
Thank you.
I had a question about the perception action communication work that you presented. I was wondering what the bottleneck was for controlling all of the degrees of freedom of the drone. It seems like some of the work that's been done looks at just two-dimensional stuff. And I was wondering if it was just the models, like the networks, weren't able to solve problems with higher dimensions, or it was just the hardware on the drones.
No, it's not a 2D versus 3D. It's more. So in each of those cases, we were trying to compare what we had done with model-based solutions, and model-based solutions don't exist except for very simple settings. So if I want to show you something works, I have to show you, compare it to something that I know works. It's as simple as that. So the flocking problem was 3D, but the other two problems, you're right, were 2D.
Oh.
So we got a new panelist because I think Daniela wanted to ask a question in person.
Actually, I just wanted to say how much I enjoyed the talk and how excited I am to see your faces on Zoom. More events like this would be wonderful.
We can't see
all of you.
Yeah, we can't see you. You didn't turn on your camera.
I don't have the option to do my camera.
Oh,
now we even lost her. Oops.
Hey,
she's back.
I just saw a comment from Shivani, and I want to second what she just said, which is I think Osama's idea was wonderful to have a panel. It feels, at least for me, it feels like I'm talking to you. We're having this discussion. So this was an awesome idea, Osama.
Yes, great idea. Does anyone have any other questions for Vijay? I have one, but I can wait since mine should have lower priority. Deanne, go for it.
I had one. Previously, some of the first slides, you showed us that evolution graphic, and I think you commented that we were, I think, on stage 2. I was wondering, in your opinion, what will be the indicators that we are crossing from one step to the next? Like, if you've thought of what the future should look like, do you have some specific indicators?
I'm sorry, you probably read too much into that picture, as perhaps Daniela did, but my main point is that as no matter who you are, if you're a young researcher, established researcher, or a professor, you're always trying to predict the future. You want to see where the field is going, and so you want to chart that evolution for you. And no matter what field you're in, you're always at an early stage. If you're not at an early stage, you're not doing research, right? So I just meant that there is some evolution, and our job is to predict where the field is going, and then try to say, well, I'm going to stake my ground in this area. And the comment I made to Daniela is you don't want to pick an area that's in the critical path of a company that's doing it for profit, which is
EJ, I have a provocative question.
Please.
The people are talking more and more about aero taxis as a replacement of regular taxis, which is a kind of a combination of driving on the road and also flying, and whether it's going to be the helicopter or drone. So the provocative question is, what do you think, which technology of this aero part will take over this aero taxi, the quadrotor or the helicopter?
Well, people, I don't know why people fixate on the quadrotor for that, presumably because you can drive this through electric motors, and presumably because battery power is electric energy is clean, but helicopters are far more efficient. So this makes no sense to me. Now I got to be careful because there are a lot of smart people that are working on this idea at Uber, at Kitty Hawk, and they obviously know something which I don't, but my instinct is that is not the right approach. I also talked to another startup company who actually does this using microturbines. So this is using fossil fuels, and of course, nobody wants to mess with fossil fuels these days, but that's a practical idea. So if you tell me you want to transport 100 kg, up to 100 kg pilot over at 50 miles an hour, or for a half an hour flight, that's doable. So again, a helicopter could also do that. This particular design that they're working on, the company is called Jetoptera, that's a tail sitter. So those are practical designs, I think. I don't know why you would go to a quadrotor.
So Vijay, I had a follow-on to Rujana's question. One of the interesting things is many parts of robotics, many of us who work in robotics use robots as a way to extract information about the environment. But one of the difficult things to do in robotics is to move mass around, right? Moving information around is not easy by any means, but moving mass around is often vastly underrated, right? And maybe this problem of moving people around seems very difficult. Even the problem of dropping off packages is non-trivial. So where do you think we're likely to see some successes in not just moving bits around, but moving mass?
So without violating the laws of physics, right?
Correct.
That's a good question. I don't know how to think about that challenge. Clearly, if you think in a grounded setting, as is the case in industrial robotics, or if you even think about legged robots, I think we've come a long way. If you look at price-performance ratios of electromechanical systems, new motors, particularly this idea that you can embed electronics to build much more sophisticated motors with inexpensive hardware. Or the grippers we've built, not we, meaning the community has built, in terms of, if Mark is in the audience, Mark Kwiatkowski, the gecko-inspired grippers. So a lot of new stuff has happened there, right? And all of those things have been grounded. So I think this idea that you want to do this from the air is just a lot more challenging. That's all I said. So again, if you want to interact with the stationary environment, you have to hover. if you have to hover, the laws of physics for hovering don't work in your favor. But I hear they're going to Mars. Maybe they'll discover a new law of physics there. So I don't know if you've heard this. So NASA is launching, JPL is not launching helicopters now to Mars, which will be interesting.
Yeah.
Any other questions? The question I had is kind of a smaller technical one, which I think I'll take on offline with Vijay. And I think probably we do have still some questions here, but we have gone nearly 25 minutes beyond when we were supposed to end. I think I need a little guidance from the IFRR bosses. Should we wrap it up? Should we keep going?
I think a lot of people from Europe, I think they would appreciate it if you wrapped it up.
They could go to bed, yeah. Okay. Oh, Osama, you can let us know. I see you. You're muted. You're muted. You're muted. Osama, you're muted. Osama, can someone unmute him?
Hi.
Osama.
Yes.
Okay, there.
Sorry. No, I said you can go for 5 more minutes. And I have a question for Vijay, by the way. It's so nice to see you all. Thank you, Daniela, for joining. Vijay, I wanted to ask you about the challenges we are going to face when we start adding lightweight arms. Maybe this is a little bit related to Gaurav's questions about, flying hands. What is going to happen? Of course, it's not going to be in the same scale of what we can do on land, but I think it would be amazing to have flying hands.
Yeah, so I do think that, if you build a mobile manipulator on the ground, the challenges are, it's simpler to do it. So in the air, one question you can ask is how many degrees of freedom do you need in an arm in order to get 6 degrees of freedom motion? The answer is only 2, because you already have 4 degrees of freedom in a quad rotor. And that's a very interesting underactuated system. And if you do this properly, the motors, as you know, some of course, can be put as close to the center of mass as possible, and you can come up with a really agile system. So, but this is less about carrying large payloads.
Absolutely, yeah.
Yeah, but to build a agile system that can catch things or just
bring
even
save the cat from the trees.
Yeah,
and,
yeah.
do all kinds of tasks. Yes, I really think this is the next important addition to, aerial robotics. And aerial robotics will really be able to do much more once we bring the capability of manipulation. And very simple interactions, very simple intervention would requires maybe lightweight arms and some dexterous hands. But that would be wonderful.
Yeah, agree.
So Nancy, I'm sure you have other questions, so you can.
I do. Okay, so you think we should keep going? Okay,
yeah,
for another
2 more minutes. Yeah, we will have.
Okay, so here's a question. How do you think academics can push industry to take more notice of problems that we think are deserving of attention or resources at the industrial scale? So how can we influence them?
I believe we already are. I mean, industry is paying a lot more attention to academics than they ever did. I think we, as a field, we attract the top talent, and industry is constantly looking at us to see what we're working on and what the opportunities are.
Cool.
So I'm not sure that is that's a challenge. It's already happening. I think one question you can ask is, how do you influence industry to work on problems that you want them to work on? And I think you do it.
Yeah, I think that's a companion question, right?
Yeah,
and,
I think
and it's also similar to the, like kind of the pharmaceutical industry problem is, why weren't they working on malaria, for example? So what are the robotics problems that are in that category, and what should we do about it?
Yeah, I think I mean you look at it in the context of COVID-19. It just we've talked about healthcare robots for I don't know how many years. Why couldn't you have robots, even teleoperated, be the first line of defense interface between human beings that needed care and medical facilities? Why did nurses have to get infected? So there are very simple things that could be done, and today doctors will tell you that. So why didn't we? Why weren't we compelling in terms of creating that vision for industry? I think there's a lot of talk of robots being used for cleaning infected areas. This is ICUs. Infections have been around for a long, long time. One would think by now you'd have figured out this problem. So these are not hard problems, and yet there's no industrial solutions to it. I was just struck by the fact that all the tele-robotics we've done over the years came to naught, and eventually what they did was they wanted an iPad on wheels that they could joystick, they could remote control. So that's what we were supplying our hospitals. By now, we should have had inexpensive products that hospitals all should have had, and they were ready to use, and that didn't happen. I mean, thank heavens for Zoom and Blue Jeans, otherwise we would have been in really bad shape. So totally, I think it's our job to try to push those technologies forward.
So you don't have, from your work in Washington, you don't have any kind of guidance on how we can nudge folks in the right way?
I think this is a more complicated problem and requires longer discussions. Happy to get into it.
Okay, so maybe another seminar. Well, I think so Osama, should we finish now?
Yeah, I just wanted to add to Vijay's comment that perhaps you have to consider also the sense of touch and the connection through haptic interaction between human and drones and objects and distributing. I mean, we can augment Zoom with haptics. Anyway, I just wanted to say thank you so much, Vijay, for the wonderful presentation. So exciting things are happening in this area of robotics. And thank you to the panelists, and thank you to the moderator, and to all the participants for their questions. Nancy?
Nothing really to add. Thank you. I think it was a great idea to add the panelists, and it made it a lot more fun, and certainly at least for us, and hopefully also for those that aren't able to be on the screen. So thank you to IFRR, and thank you to Vijay again.
Thank you guys. Thank you for the honor.
We can unmute and give a little clap now.
Thank you.
Thank you.
Bye.